Hey guys, welcome back to the AI Snack Zone, where we're going to be covering weekly papers in ML and AI that I find interesting or that are relevant in the field. For our second video, we have a little bit of a rebrand here, new AI art to help us with our journey. And yeah, let's get started. So today's paper we're going to be covering is BERT by Devlin et al. 2019. And I'd say this is our second step in the journey of understanding how LLMs came to be today after last week's covering of transformers. And I have a picture of Bert from Sesame Street. And our one sentence key idea of the paper, or our OSCE of the paper, is that BERT learns to bidirectionally understand language by guessing missing words and predicting sentence order. And here we see OSCE cosplaying as BERT on Berkeley's campus. So let's get started with motivation. Why did they do this? So we have to go over a little bit of background here. Prior to BERT, a model by OpenAI called GPT came out, which was trained unidirectionally, left to right, which basically means that the model was only trained to see sentences from the left to the right direction, which BERT argued limited representation power and made the model biased towards one direction. I've illustrated a quick example here to show why this might be. Our example sentence is, "He sat by the bank and watched the water flow." And if we look at the word bank, we see that up until here, we might assume that "he sat by the bank" refers to this. But after reading the entire sentence, we can then infer that bank actually refers to a riverbank. And it requires analyzing the entire sentence to know this, not just in a unidirectional way. And prior to BERT, there are also things called feature-based models. And the most famous one was Elmo. And I know you probably see some naming similarities here. Elmo was a two-layer bidirectional LSTM architecture. And it basically layered one left-to-right LSTM on top of another right-to-left LSTM. And the primary difference between Elmo and BERT was that Elmo's model embeddings, or its last layer's weights, were extracted as features for specific tasks, while BERT's model is instead fine-tuned for these tasks. Elmo was much less scalable than BERT because it used a recurrent neural network called an LSTM instead of a transformer. And we covered why RNNs are much less scalable than transformers in last week's Snack Zone. And another primary motivation for BERT was this idea of something called transfer learning, which was the concept that pre-training a model on a general task using a huge data set, then fine-tuning it to a specific task was very successful in the past, especially in computer vision. Some examples of this was AlexNet and ResNet, which were trained on the large ImageNet database, but then fine-tuned to do specific things. Now we can go to innovation. So BERT's primary contribution was that it was a deep bidirectional network. BERT learned from both directions simultaneously. BERT utilized the transformers encoder architecture to do so. And we can see that this bidirectional training was enabled by something called masked language modeling, which we will cover in the breakdown section. And BERT also gave us the idea of a unified pipeline, which showed that one pre-trained model could be fine-tuned for multiple tasks. BERT's base model was fine-tuned on many different things like classification, NER, which is named entity recognition. For example, in the sentence, "the cat sat," we can identify that cat is a noun and sat is a verb and the is an article. Also, just basic things like question answer. BERT showed that we only need to change the final layer of the model architecture to fit accordingly to the task at hand. And it showed us that one model can achieve state-of-the-art performance across a wide range of NLP benchmarks, and gave us the idea that transfer learning also applied to these language models. Okay, we're ready to go to the breakdown. So, what is BERT's model architecture? BERT was a multi-layer bidirectional transformer, as we covered already, and it was based on the encoder-only part of the paper Attention Is All You Need. They trained two different BERTs with different sizes, so they have this base model, which has the same parameter count as GPT to do some comparison tests, and also a larger model with more heads and more layers. Most of the time, how we compare models is how many total parameters it has. So we see that the base model has 110 total parameters and the large one has 340. And for comparison, models today that are used have many billions of parameters. So just 6 years ago, we were using much smaller models for our computation. The training pipeline for BERT looks like the following. So we have this pre-training process where BERT learns general language ideas, and then we have a fine-tuning process where BERT learns to generalize to specific tasks. Pre-training is where we train a model on a huge, large, unlabeled text corpus. The objective of pre-training is to learn a general language understanding. It produces a general purpose model that can be adapted to many different things via fine-tuning. The core concept of pre-training is that it's self-supervised learning, which means that labels are not required, and BERT simply just runs through this whole huge corpus of data to get better at its goal. So the two pre-training tasks that BERT was trained on were masked LM and next sentence prediction, and we'll run through how each of these works. Okay, let's go over quickly what the MLM task is. So in our example, I have an example sentence: I ate a chocolate chip cookie and it was tasty. Basically, what the model sees is some percentage of the words in the sentence are masked out. They are taken away. So let's say chocolate is taken away, and was is taken away. What we want the model to do is, from this input, we want the model to try to predict the tokens that go in those positions. That's basically what the MLM task is. Now, there are a few technicalities. So 15% of the tokens in each sentence are selected for masking. And of these 15%, 80% of them are replaced with something called a mask token. Let's say chocolate chip cookie turns into this. The word chocolate is just replaced with mask. It is analogous to what we did up here. 10% of these mask tokens are replaced with a random token. Chocolate chip cookie becomes amnesia chip cookie. So chocolate here is replaced with some random word. The final 10% are unaltered. Chocolate chip cookie is chocolate chip cookie. And why do we do this, you might ask? So this basically prevents the model from overfitting to the mask token. This way, in like real text, BERT doesn't only look at like a mask token to really understand what a word is or what it should be. Regardless of what the word is replaced with, these indices of missing words are marked beforehand, and BERT has to predict what they are either way. So some of the time, BERT sees all the words, but has to still predict that the words are correct. Let's say index 4 is marked in the sentence. Regardless of whether it says mask, amnesia, or chocolate, we still have to predict using the entire sentence what that word actually should be. So the prediction objective of BERT for this MLM task is, for each masked token, BERT outputs a probability distribution. The loss for each of these examples is computed using cross-entropy. If you forget the formula for cross-entropy, it's just the loss, the MLM loss at position I, token position I, is equal to the negative log probability of the correct token, which is WI. And the total MLM loss for a prompt is just the average, or the sum, of all of these mask tokens. Okay, great. So now we can move on to the next task, which is next sentence prediction. So in NSP, the goal is to predict, given a pair of sentences, predict whether the second sentence, sentence B, logically follows sentence A using a classification head. So the input format is basically we have the CLS token, which I'll explain in detail later, but for now it's the start of each pair of sentences. And then we have sentence A's tokens, then we have a separator token, which separates the sentences, and then we have sentence B's tokens, and then the final separator token. Half the time, sentence B follows sentence A logically. In this case, the label for this pair is next. And the other half of the time, they have no relation. Sentence B is a random sentence from the corpus. In this case, the label is not next. And yeah, using the text corpus, the model just picks random sentences. Half the time, the second sentence is actually the continuation of the first sentence, and the other half of the time, it's just a completely random sentence. Let's go over quickly how it does this. The key is in the CLS token. So the CLS token is just like any other token in the sentence. It has its own hidden state. After backpropagation, its final hidden states will contain information about the entire sentence. And this is, remember, thanks to self-attention that we covered last time in Transformers. So after the model runs through the entire example, the CLS token will have encountered the attention scores of every other token in the sentence. This final hidden state will be then passed through a final classification layer to predict if the sentence is next or not next. And the loss function that NSP uses is also cross-entropy loss. So yeah, that's MLM and NSP. I think these are really intuitive tasks that the language model can take on. So MLM helps the model understand contextual embeddings of tokens, like do these tokens or how do tokens relate to each other? While NSP allows the model to make sentence level decisions. So does sentence B follow sentence A? Or do two sentences relate to each other? Lastly, let's look at how the model actually trains on NSP and MLM at the same time. So to combine MLM and NSP during pre-training, all inputs will have the format that we saw for next sentence prediction. First, the masking happens, just like in MLM, but this time across the entire example, so the pair of sentences. And then NSP is predicted on this mask example, and MLM predicts tokens at the same time. Final loss is just simply a sum of the NSP loss and the MLM loss. Yeah, this combination allows BERT to not have to run through two training pipelines, but instead just one pass through the entire training process on both tasks at the same time. And also there's a side note. So I have this picture of BERT's input representation. There is one difference between BERT's input embeddings and the normal transformers. BERT adds something called a segment embedding, which differentiates each word from belonging to sentence A or sentence B. For BERT, input embeddings are just a sum of token plus positional plus this new thing called a segment embedding. Okay, and I think it's time for a snack break. Today's snack break is actually in SF at Urban Ritual. Urban Ritual is probably my favorite boba spot in SF, and I would definitely recommend you go if you are in the area. And my favorite drink from Urban Ritual is mango sticky rice, and I really miss it down here in SD. But I'm going up to SF actually next week, so hopefully I can get some. But yeah, shout out to Urban Ritual. I think it would be a perfect thing to drink while you listen to this AI Snack Zone. And if you don't have an Urban Ritual near you, just grab a coffee and we'll be on to the next part of our breakdown. Next, we're going to go over what fine-tuning is. Fine-tuning is basically just taking that base model that we learned from pre-training and adding a small task-specific layer to the model. Fine-tuning requires much less data and training time than training from scratch, and it's an example of transfer learning where we can take the whole model that BERT learned from MLM and NSP and adapt it to different tasks that we might want. In the paper, they first fine-tuned it on GLUE, which is basically a set of 8 and I think now 9 different tasks that evaluate how much of a grasp a model has on general language. So I have a list of the 8 tasks that they trained on here. I won't cover each of these individually because we'll cover the other tasks, Squad and Swag. But you can see here that each of these tasks has a different concept attached to it. So we have things like sentiment or similarity, and also paraphrasing, inference, and etc. I encourage you to look at the GLUE benchmarks and understand them for yourselves. But what we will cover is Squad and Swag. So let's dive a little bit deeper into what Squad is and how it was used to benchmark BERT. My goal in giving you this example of Squad is to show you how these models are being fine-tuned today. In Squad, which is the Stanford question and answering dataset, the input is a question along with a passage. So the goal is to predict which section of the passage answers the question at hand. To do this, we've introduced 2 new vectors, the start vector, which is S, and the end vector, which is E. And these vectors are learned weights. How they're used is the probability that the passage starts at token position I is equal to the softmax of S.ti. And Ti is the final layer output representation of token I. And the probability that something ends at position j is equal to, I think this is predictable, the softmax of the end vector dot tj. And tj is the final layer output at position j. And we define something called a score function. So the score of a pairing ij equals s dot ti, which we can see here, plus e dot tj. What we do is simply loop through all j more than I, so all possible pairings of I and j, and take the pairing with the highest score as our answer. And yeah, simple as that. And the objective is to maximize the log likelihood of the correct start and end positions. And this is using cross entropy. So we add this final two vectors that are learned, just backpropagate using this loss function, this objective function, over the entire model, changing the model's weights and also the vector's weights, to finally receive a fine-tuned model that is specified to perform well on this task specifically. Squad 2.0 enhanced this by adding a case where the answer to the question is not inside the passage. And this is where if I equals 0 and j equals 0. So Squad 2.0 basically just generalized this case a little bit more to real world problems. For the last task, swag, the goal was given a sentence, choose the most plausible continuation among 4 choices. And for each option, we create an input, sentence A plus sentence B. So what happens when fine-tuning swag is the process is basically the same as squad. So remember the CLS token from before, which represents like a summary of the whole sentence. We use a dot product of C and V, which is a trainable vector, much like S and E in this example for squad. V is also a trainable vector, which is updated using backpropagation. And we assign a score, which is the dot product of C and V. We apply a softmax over these scores to predict the best continuation. For every fine-tuning task you encounter, the process is basically the same. You first find an appropriate dataset, define some sort of output head, whether it be classification or like a vector like this, train the model. So once you do these 3 steps, you'll have a model that weights are updated to be according to your task, and it'll perform better at your task. Let's, of course, go over the results. So how did BERT perform? If we look at the GLUE scores, it outperforms every prior model significantly. Even the base BERT already outperforms everything, and the large BERT outperforms everything by a huge margin, like 7%. For Squad and Swag, the story is the same. It outperforms every state-of-the-art model, and it also additionally outperforms humans on specific tasks. And some ablation studies showed that BERT also performed worse without next sentence prediction training. But I have to add a note here that NSP was refuted by later works such as Roberta. But more significantly, BERT performs a lot worse with just LTR, so unilateral left to right representations like GPT was. Without bidirectional training, it's a whole 10% less. BERT's main idea was that it is important to have these bidirectional relationships. Okay, and let's go over the impact. So obviously, as we saw in the results, BERT dominated benchmarks at launch. And as a result, it became the baseline for a huge family of new models like Roberta, Albert, Distilbert, and etc. And I've added an AI-generated picture of Oski as BERT lifting some weights. So it was the first work to self-claimingly demonstrate convincingly that scaling to extreme model sizes also leads to large improvements on very small scale tasks. And this is a direct quote from the paper. It was also one of the first works to popularize transformer-based pre-training and fine-tuning, which is the standard today. So let's go over the future. What came after BERT and what comes next? So BERT led to a multitude of other variants and improvements. So we have Roberta, which removed next sentence prediction from the pre-training pipeline and trained for longer on more data, which led to an improved performance. We have Albert, which reduced the parameter count via weight sharing and resulted in a lighter model with similar performance. And we have multiple architectures like Distilbert, TinyBERT, MobileBERT, which aim to shrink the model size through various methods for edge devices like your phone or your laptop. And there are also a huge amount of domain-specific architectures like BioBERT, SciBERT, and CoBERT. Even though GPT dominates for text generation, BERT is still the go-to model for encoding tasks like RAG or embedding generation. New research in this field focuses on things like encoder-decoder hybrids and using BERT-like modules within larger systems to help with RAG, embedding, fetching, and stuff like that. New research also has shown a shift from these pre-train then fine-tune methods towards a pre-train then prompt engineer method. And that's really where the research today has been trending towards. So yeah, that's all for BERT. Here are a list of references that I used throughout the presentation to help me compile all this information. Thank you guys so much for watching this episode of the AI Snack Zone. Make sure you like and subscribe for more. I'll try to upload once or twice a week. And you can find all my information on my website listed on the screen. Thank you guys for watching again, and I'll see you guys next time. Peace.